We always imagine life needing water, but the universe may have stocked its oceans with methane instead, and filled them with creatures beyond our strangest dreams. In our recent episode on colonizing rogue planets, we explored how civilizations might build homes on worlds cast adrift in the dark. That got me thinking more broadly about ecosystems that exist without sunlight, leading to an episode on dark biospheres, where we looked at a variety of exotic habitats. Among those, we touched on the intriguing possibility of life lurking beneath the icy crusts of moons orbiting giant planets. I also noted there that while ammonia tends to be a top-tier candidate for alternative biochemistries or solvents, methane and other hydrocarbons also have a lot going for them. It also made me think of Titan, the only moon we know of with an actual atmosphere, and thus where surface life using sunlight might be possible. While we typically associate methane with dark, frigid places, like Titan's hydrocarbon lakes, there's no rule saying you wouldn't pair methane chemistry with a bit of sunlight, crafting alien biospheres every bit as rich and varied as Earth's. And so today, I thought methane deserved its very own spotlight. We'll explore what life might look like on worlds with methane oceans, whether complex ecosystems could evolve there, and what such discoveries would teach us about the breadth of nature's imagination. So, grab a drink and a snack, hit those like, subscribe, and notification buttons, and let's dive into the methane seas to see if they could hold life. Titan and methane oceans, the basics. When we talk about methane worlds, the poster child is always Titan, Saturn's largest moon. Roughly half again as large as Earth's own moon, Titan boasts a thick, nitrogen-rich atmosphere suffused with methane, so dense you would need a pressure suit to walk on the surface. Indeed, the pressure is about half again that of Earth's, and more interestingly, the air density is about 4 times higher. Nor is it around room temperature. You would need an oxygen mask and a very heavy coat, since the temperature hovers around minus 180 degrees Celsius. For specifics, that's 93 Kelvin or negative 292 Fahrenheit, surface pressure 1.45 atmospheres, and a density of 5.3 kilograms per cubic meter. Now, like Earth, most of that is diatomic nitrogen, indeed even more so. It runs somewhere around 95 to 98% nitrogen. It varies by season, with most of the remainder being methane, a smidge of diatomic hydrogen, and trace amounts of ethane, diacetylene, acetylene, propane, and hydrogen cyanide. So again, not a place you want to breathe in, and even an insulated dome filled with oxygen could be worrisome since so many of those are unhealthy or flammable substances. As we discussed in colonizing Titan way back, it has a lot of interesting resources that tempt us to settle it, but if we were settling the surface in a big way, it would likely be with post-biological life. Giant server farms enjoying the ultra-core the environment permits. That thick nitrogen atmosphere might be very useful for terraforming Mars or filling space habitats, as nitrogen is rather rare in the inner solar system, and besides Earth, the only other big source is Venus, which has nearly as big a gravity well as Earth and enjoys other difficulties when it comes to extracting resources from it. But Titan is remarkable for another reason. It's the only other place in the solar system besides Earth known to have stable liquids on its surface. Only instead of water, its rivers, lakes, and seas are filled with liquid methane and ethane. Methane even rains from orange clouds, carving landscapes eerily similar to those on our own world. It's a strange mirror of Earth, a place where methane plays the role water does here, flowing in vast networks of channels and pooling in broad seas like the Kraken Mare, which is larger than the Caspian Sea. From orbit, it almost looks familiar, until you remember you're gazing upon a realm where liquid hydrocarbons dominate the hydrological cycle. And Titan may not be unique. As we catalog thousands of exoplanets, we're finding hints that methane-rich atmospheres and frigid conditions might be common, especially around smaller, cooler stars or in the outer reaches of planetary systems. Some of these worlds could be super Titans, with even deeper seas of liquid methane. There may be a lot of cool worlds and exomoons out there where life could potentially emerge. So today, we'll dive into the alien chemistry of such places, pondering whether life could not only exist, but perhaps flourish in ways as rich and complicated as Earth's jungles or coral reefs. Could methane oceans cradle ecosystems with their own predators and prey, or even spark intelligences gazing up their hazy skies, dreaming of more? Chemistry of life, beyond water. When we imagine life elsewhere in the universe, we tend to assume it needs water. That's perfectly understandable. On Earth, water is everywhere life is. It's the solvent that carries nutrients, facilitates countless chemical reactions, and stabilizes large, complex molecules like DNA and proteins. Water is remarkably good at this because of its polarity and the way it forms hydrogen bonds, allowing it to dissolve a vast range of substances. It also stays liquid over a generous temperature range, from 0 to 100 degrees Celsius at standard pressure, which is quite friendly for chemistry. Generally speaking, you can only have liquids if you have pressure. It's the nature of matter. It would tend to clump together and be held together by normal intermolecular forces, but if you heat it up, that internal motion and vibration eventually breaks those bonds, scattering individual molecules out as a gas. Keep heating it up, and eventually those molecules break. Those individual atoms start ionizing and become lone nuclei stripped of their electrons. But at temperatures that turn a solid into a gas, in a vacuum, what we call sublimation, having a bunch of other matter near it shoves those molecules back at ambient pressure, resulting in that in-between state of liquid. The higher the pressure, the higher the temperature range something can exist as a liquid. That's why if you put water under pressure, like we do in steam engines and turbines, you can raise that boiling point. If you reduce that pressure, you can get water to boil at room temperature. Conveniently, water is a liquid at the temperature range and pressure range that makes a lot of chemistry possible in it, as for instance it wouldn't be very handy to have a solvent that was only a liquid at temperatures that destroyed sugars and starches. It's also incredibly common, as oxygen is the most abundant element after hydrogen and helium, and hydrogen and oxygen make water. There are often issues with chemistry at higher temperatures or pressures, so do not assume a planet with a much higher surface pressure than Earth can have life at higher than normal boiling point. But water isn't the only solvent in the cosmic pantry. We've already noted ammonia as a good one. We have a whole episode discussing that, and it is made of hydrogen and nitrogen, another common element, but is liquid at sub-zero temperatures. Ammonia has a boiling point of negative 33.34 Celsius, negative 28.01 Fahrenheit, and 239.81 Kelvin, and a melting point of negative 77.73 Celsius, negative 107.91 Fahrenheit, 195.42 Kelvin. But water and ammonia are not the only common hydrogen-bonding simple molecules. Carbon, another ultra-abundant element, forms with hydrogen to make methane and other hydrocarbons. Methane has a boiling point of negative 161.5 Celsius, negative 258.7 Fahrenheit, 111.6 Kelvin, and a melting point of 182.5 Celsius, negative 296.5 Fahrenheit, or 90.6 Kelvin. At Titan's frigid temperatures, methane is liquid, abundant, stable, and behaves a bit like water does here. It rains from the sky, flows in rivers, and carves channels. It's hard not to wonder, could methane serve the same biological role? Since we are talking some chemistry in this section, let's explain what a hydrocarbon is really quick. A hydrocarbon is an organic compound made entirely of two elements, hydrogen and carbon, as the name implies. When you burn these with oxygen like we do with natural gas, propane, gasoline, and diesel, you usually get carbon dioxide and water as main byproducts. These molecules form the backbone of most organic chemistry, so probably bear discussion. Simple chain hydrocarbons begin with methane, 1 carbon and 4 hydrogen atoms, and we can keep adding another carbon atom and 2 branching hydrogen atoms to make bigger hydrocarbons. Big ones are basically a millipede with a line of carbon for a body, and a hydrogen on each carbon atom's side for a leg, and one at the front and back as head and tail. Methane is 1 carbon, 4 hydrogen, ethane 2 carbon, 6 hydrogen, propane 3 carbon, 8 hydrogen, butane is 4 carbon, 10 hydrogen, and when we get up to octane, 8 carbon, 8 times 2 plus 2 hydrogen, or 18 hydrogen, and that keeps going. We also have branched structures, or even complex rings like benzene, which is an inner hexagon of 6 carbon atoms, each with the hydrogen branching outward from them to form a second hexagon, or cyclohexane, which is similar but has a pair of hydrogen atoms sticking off each carbon atom. These hydrocarbons, along with water, form the basis of life here on Earth, and water's main role is as a solvent. Thus, we could imagine liquid methane serving that alternative role at lower temperatures. Sounds good, but there are serious challenges. Methane is non-polar, meaning it doesn't dissolve ionic compounds or facilitate charged reactions the way water does. Chemical reactions in such a solvent would be sluggish, partly because of the cold. At Titan's negative 100 degrees Celsius, reaction rates are orders of magnitude slower than at Earth's temperate oceans. Life might still emerge, but would do so on a much longer clock. Mind you, a bigger planet might have much thicker atmosphere, and at 5 atmospheres of pressure, you can get liquid methane at negative 128 Celsius, negative 112 at 10 atmospheres. That's still ultra cold, and those higher pressures might bring other problems to life, but the combination might help to make that life a bit less sluggish and quicker to form and evolve. Still rather difficult, and as is often the case when we look at alternate chemistries for life, we start seeing why when we talk about the Fermi paradox, we often tend to assume, especially for looking for alien technosensors, that life, or at least very complex life, tends to come from water worlds. Yet methane brings intriguing possibilities. Laboratory models have suggested that the azotosomes, membrane-like structures made from nitrogen-rich organic molecules, could form in liquid methane, much the way lipid bilayers form in water. These could theoretically act as cell walls for methane-based life. Cell walls are vital to any nascent life, as is what lets you make different chemical solutions than the ambient solvent around you and keeps you from dispersing into it. And while we often pair methane with dark, cold places, it doesn't have to be that way. Ignoring that methane is perfectly common on Earth and highly involved in our own water-centric chemistry, especially as a building block for hydrocarbons, it's got options. Again, a world just a bit warmer than Titan, orbiting closer to its star, might still keep methane oceans under high atmospheric pressures. There, photochemistry could play a role akin to photosynthesis, harvesting starlight to drive the slow machinery of alien metabolisms. Even on Titan itself, energy might come from tidal stresses as the moon flexes under Saturn's gravity, sparking chemical disequilibria that primitive life could exploit. Alternatively, occasional impacts or cryovolcanic eruptions could inject heat and new materials, sustaining local hotspots of chemistry. All told, while methane isn't as versatile as water, it is abundant, it has a low freezing point, and it can still form a medium where carbon-based molecules could drift, collide, and perhaps assemble into something more. It paints a vision of life evolving at a glacial pace, in seas so cold they'd flash freeze our cells, yet still finding a way, slow, patient, and utterly alien. Could life evolve there? So, could life truly evolve in these alien seas of methane, or would they simply remain sterile pools, forever churning under orange skies with nothing more complicated than drifting hydrocarbons? In many ways, evolution on a methane world would play by the same fundamental rules it does here on Earth. Chemistry would still favor complexity in places where energy flows, where there are gradients to exploit, and where molecules can bump into each other often enough to try out new combinations. The key difference is the temperature. Colder temperatures slow everything down, from reaction rates to the metabolic churn inside a hypothetical organism. That doesn't necessarily preclude life. It just means that we might be looking at a biosphere evolving on a geological clock, where what might take millions of years on Earth could take hundreds of millions or even billions on Titan-like worlds. Evolution would proceed, but in a kind of slow motion, with each new innovation unfolding over epochs. Conveniently, the universe is a lot older than Earth. As we discussed in other episodes, while rocky, heavy element-abundant planets are more common now than in the past, we could probably have some even 10 billion years back. Moreover, low-density and lower-gravity icy planets open the door to cryovolcanoes, moving materials back to the surface from potentially deeper down than on Earth, so such worlds might have been life possible long before Earth was. Energy is always the limiting factor. On Earth, most life ultimately draws power from the sun, with photosynthesis capturing photons and building up sugars to feed everything else. Even in our darkest oceans, deep-sea creatures rely on nutrients trickling down from above, or on chemosynthetic microbes feeding on chemical gradients around hydrothermal vents. Could methane worlds offer similar footholds? Possibly. Titan's surface might be only dimly lit by the distant sun, but there's still light, enough in theory for some sluggish form of photochemistry. Alternatively, life there might latch on to tidal flexing, as Titan is constantly squeezed and stretched by Saturn's immense gravity, generating internal heat and driving pockets of chemical disequilibrium. Or it could rely on slow, steady release of energy from cosmic rays or impacts, or localized heating from cryovolcanic activity. Those closer to the galactic core or inside old red globular clusters might get more ambient radiation. Moreover, a planet with higher gravity than Titan could maintain a higher pressure atmosphere and liquid methane as close as half Titan's distance from the sun, and that is plenty enough sunlight for even terrestrial plants to grow off of, especially the ones that are adapted for shade. So if they can get a photosynthetic biology in place, they have all the energy they need. Their real limitation is on expending it without overheating that methane. Perhaps they develop powerful radiators to help stay cool while their metabolism functioned, as we have. Amusingly, much as oxygen, once a poisonous waste product of primordial life on Earth, eventually became critical to life functioning, I could imagine an environment like this adapting life forms that ran on ammonia or water solvents and had thick insulating hides to let them use sunlight and function quicker and more energetically. Of course, this would only be plausible if you had bigger life forms. So the bigger question is whether such worlds could go beyond simple microbe analogies. Could methane oceans spawn their own equivalent of predators and prey, of grazers and hunters, of ecosystems cycling nutrients and energy in intricate webs? It's tempting to think so. Once evolution gets rolling, complexity tends to pile up wherever there's competition. The harsh, cold environment would favor adaptations very different from anything we know. Life there might move slowly, perhaps only stirring to feed or reproduce once every few Titan days, which last over 16 Earth days each. Still, in the grand sweep of time, even glacier-paced metabolisms could branch out into startling diversity. Given enough eons, perhaps even intelligence might stir beneath those methane waves, creatures with chemistry alien to ours, pondering their own mysteries under salmon skies. Imagining alien ecosystems. Let's go ahead and let our imaginations off the leash for a moment. Suppose life does take hold in these methane oceans. What might such an alien ecosystem actually look like? It may float. Titan's atmosphere is mostly nitrogen, but it's abundant in hydrogen, as methane and hydrocarbons, but also as diatomic hydrogen, which is vastly lighter than nitrogen and this can be used as a lifting gas just on Earth. But buoyant life forms floating in the air has some advantage in a thicker atmosphere or lower gravity, and both would be true here. Indeed, their internal heating from metabolic processes might help with that buoyancy, much as hot air balloons function. How about in the methane seas, though? Picture vast glassy seas of liquid methane stretching to the horizon under a hazy copper sky. Instead of blue waves catching sunlight, you'd see dark, oily ripples gleaming under a distant pale sun, or perhaps on the ghostly glow of Saturn's rings that was still on Titan. The atmosphere would be thick and syrupy compared to Earth's, carrying organic smog that filters the light into deep ambers and burnt oranges. Near the surface, we might find drifting mats of simple hydrocarbon life, the methane world equivalent of plankton. Tiny cells or vesicles, built from a cytosome-like membranes, could float just below the surface, absorbing stray photons or feasting on chemical gradients stirred by winds and tides. Maybe these microscopic drifters glow faintly with bioluminescence, signaling to each other in pulses of green or violet across the gloom. Go deeper, and life might take on more substantial forms. Slow, lumbering swimmers could prowl the twilight layers of the ocean, their metabolism so sluggish that a feeding frenzy might unfold over hours or days. With such limited energy, motion itself would be precious. Predators, if they existed, might spend most of their lives dormant, waking only when chemical signals suggest prey is near. Imagine massive filter feeders trailing tendrils through the dark methane, sifting for nutrient-rich organics, or serpentine grazers inching across the seafloor, scraping up clumps of more sessile life, perhaps anchored colonies that pull vital molecules from the current. And of course, no alien ecosystem speculation is complete without a touch of eerie light. In an environment starved of warmth and sunlight, bioluminescence could become a dominant strategy. Creatures might pulse with slow, haunting glows, either to lure prey, warn off rivals, or communicate across the murk. Entire mating rituals could be built on dazzling rhythmic light shows rippling through the methane gloom. Could such worlds produce intelligence? It's hard to say. Energy is scarce, reaction times are long, and environments like these might favor patience over curiosity. Yet life is endlessly inventive. If evolution stumbled on a way to process thoughts slowly, to pass down knowledge chemically rather than electrically, or to build long-lived, methodical cultures, there's no fundamental reason why even the frigid methane seas could not someday give rise to minds pondering the same cosmic mysteries we do. We spend a lot of time talking about alien life forms or humanity's future, and it's easy to forget just how much of our own society is shaped by our lifespan and maturation rates. Change those and you change everything. A species with a very different lifespan would likely have very different economies, since what's practical or efficient shifts with generation length. Schools, pensions, retirement, babysitting, not exactly glamorous topics, but they are critical to how any society functions. That's the focus of my latest monthly exclusive episode, The Economics of Immortality. What happens when the rarest thing in the universe, time itself, is no longer scarce? Join us as we explore how immortality could reshape the societies of tomorrow. That's out now on Nebula, the largest creator-owned streaming platform where every episode of SFIA is available early and ad-free, and where I've been posting full-length exclusives like this one every month for years, along with extended editions, bonus content, and more. It's also home to amazing originals and exclusives from many other creators across science, history, and philosophy, and more, so there's always something thought-provoking to discover. Get a lifetime membership, normally $500 for just $300 by using my link, go.nebula.tv/IsaacArthur, and unlock everything forever, or get an annual plan for 40% off, $36 a year. That's 12 months for the price of 7. Scan the QR code or click the link below to start watching now. Head to go.nebula.tv/IsaacArthur to join and start watching exclusive content like the economics of immortality. Challenges to habitability. Of course, there are plenty of reasons to doubt these methane oceans teem with life. Titan's surface is a harsh, punishing place. Methane is stable there only because it's so cold, but even slight shifts in temperature or atmospheric pressure could freeze those seas solid or let them evaporate into the haze. Over millions of years, Titan's own methane is expected to dwindle without some internal process replenishing it. Then there's radiation. While Titan's thick atmosphere shields the surface from most of Saturn's charged particles, it lacks a strong magnetic field of its own. Life on Earth is helped immensely by our magnetic bubble deflecting cosmic rays and solar winds. Methane-based life might need to rely on sheer distance from its star or on chemical resilience we can only guess at. Given that it also needs to be rather cold, that's not quite as big an issue, but this is definitely a Jovian to Saturnine level of lighting. Even a planet decently bigger than Earth is likely to have enough geothermal heat on its own to keep methane liquid rather than frozen, so we are talking about moons orbiting planets with tidal heating, probably with anemic magnetospheres of their own, or planets close enough to their sun to be getting a decent high flux of solar wind, which risks stripping atmospheric hydrogen. Ultraviolet light is also brutal on methane, causing it to break up, which can let it reform into other bigger hydrocarbons, which is good, but also makes hydrocarbons in it vulnerable to atmospheric loss. As an upside, it's also quite likely there are many more planets outside the classic liquid water habitable zones than in them, or in the hotter inner zones, especially since the majority of stars are red and orange dwarfs, which are not that much less massive than our own sun, and thus can hoard planets nearly as easily, but which have far smaller habitable zones because they produce way less light. For instance, a star with 14% of our sun's mass would produce only about 1% as much light and have a habitable zone just 10% as wide as ours. It would also produce a spectrum much heavier on infrared and much lower on ultraviolet. Implications for the search for life. Still, even if life is unlikely on Titan itself, such worlds expand our sense of where to look. Methane-rich planets and moons might be common across the galaxy, especially orbiting cool stars where ice giants and their moons can form easily. That means if life can arise in methane oceans, the universe might be teeming with ecosystems utterly different from ours. Probably simpler ones where no technocentra will emerge, but life, by definition, alters its environment to live, and thus produces biocenters which we might spot in the atmosphere and the spectrum it absorbs, reflects, and emits. So, what would we look for? Subtle shifts in atmospheric composition, seasonal changes in haze, or chemical imbalances that hint at metabolism. These are the signatures we'll seek with future telescopes. Closer to home, one day we might drop submersibles in Titan's sea to taste the hydrocarbons directly, hunting for even the faintest whiff of alien biochemistry. In the end, methane worlds remind us just how parochial our thinking can be. We look for water, for Earth-like temperatures and pressures, because that's what we know. But nature may be far more adventurous. If life can write its story in methane, crawling or drifting through seas cool enough to crack steel, then how many chapters of biology are we missing simply because we didn't think to turn the page? So let's keep wondering, keep searching, and keep expanding our idea of what's possible. After all, the universe has a way of surprising us, and I suspect it still holds more alien oceans and stranger forms of life than we have ever dreamed.